So for example, one of the maps, what does that say? I'm sorry? Oh, I see. Oh, very nice. Okay. I won't erase that. Be very careful. All right. Let's see. So let's imagine we're in the plane and we just remove all points. Not all points, sorry, some collection of points. So I give you a finite set of points and I say these points are obstacles, right? So I can define a set of environments which is all subsets of R2. So in other words, you can move anywhere you want inside of R2 here, right? The only places you cannot be are at these points. And there's a finite number of them, let's say. So that would be another set of possible maps, right? Yeah, what are the good ones? Oh yeah, non-overlapping disks. So maybe instead of points, I make environments. These are very helpful to make. You know, they're very nice kinds of things. As computational geometers, you think like this all the time, right? You find a good collection of primitives, right? Are we dealing with simple polygons, polygons with holes? Maybe we have a bunch of disks, right? Let's say non-overlapping disks. Maybe they're different radii. I don't know. I'm sure you all know what happens with overlapping disks. I think it makes a mess of some kind, right? In computational geometry, I don't remember. One of those arrangement problems. So we have a collection of disks. So I could say, well, your map, your unknown map, is the set of all free spaces that I get by removing a finite set of disks of varying radii, whatever radii you like. Right? I think it's pretty reasonable. I can make those convex sets if you want. I can remove polygons from there. In other words, I can make the free space be unbounded, but have bounded polygons that I remove. Sometimes this one's helpful for the analysis and things that we do. I could say that it's a collection of piecewise analytic subsets of R2. So in other words, they're piecewise smooth, but in addition to being piecewise smooth, you can't have weird stuff like this, where you have an infinite number of wiggles. So piecewise analytic, if you remember the definition of analytic, it will imply that you only have a finite amount of changes, so that you can make smooth-looking versions of polygons, and that may be fine for a lot of problems. So I did some work before on a pursuit evasion in curved environments, or piecewise smooth environments, and really it's just a piecewise analytic environments, and it reveals a lot about the structure of the problem, which comes down to inflections and bitangents and such. So all of these are reasonable kinds of models that I like, let's say, for possible fancy Eve, a set of all environments. And I think all of these should feel appealing to computational geometers, right? These are the kind of models that we tend to like. I think, right? Maybe just being friendly. Okay, I think so. All right. So what happens for the state space for these gigantic collections here? Well, they look the same, right? So I gave you this example back here with just 5 maps, right? But what's the difference? The set fancy E is just bigger, that's all. So it's going to look the same. That's the way to think now, right? So it's going to look the same. I could have an infinite family. Oh, no, I have the infinite family of maps. So I have this really large E, but there's no difference. It's all pairs Q comma E, in which QX and QY are in E, and E is in fancy E. So for example, the state space might look like this. It's a subset of all positions, that's R2 cross S1, cross E, which is all possible maps. That's enormous, but that's okay, because we're not going to compute directly over it, right? However, I will say something interesting. So I have a lot of colleagues who are in love with probabilities. You know, they want to immediately put Bayesian models on everything, right? Computational geometers usually don't like doing that too much, I think, but there's randomized algorithms, which are very valuable. That's sort of different from what I'm talking about here. Imagine how difficult it might be to put meaningful probability densities over that space, right? So that already, when I define a big space like this, oh yeah, I put a probability distribution over the set of all piecewise analytic subsets of R2. That's problematic if you've played around with these things, right? There's some measured theoretic difficulties and such. Aside from even coming up with a reasonable prior, right? You always need a prior distribution when you do probabilistic models. So what I want to say is that I'm defining a huge space here. I'm not going to put probability densities over it, so I can comfortably define ridiculously large spaces. And I'm going to do some mathematical analysis on those, and it's going to be fine. And most of my control theory colleagues, maybe sometimes robotics, they really want the state space to be a manifold because they're going to do differential equations on it. They would like it to be a differentiable manifold. I don't care here. This is not a differentiable manifold. This set, this crazy collection of, say, piecewise analytic subsets, or the collection of all disks here, I don't want to make that into a manifold. Some good math people can make these into manifolds, I'm pretty sure, but I don't, at least topological manifolds are pretty reasonable to make from them. But I don't care. That's not important to me. So a lot of people, when they see these spaces I define, they think, what, aren't you being ridiculous here? Isn't this immediately useless? Because you can't put probabilities on it, and it doesn't look like a manifold. And I will say that's fine, because we're not going to do that stuff. Right? So we're going to do something different. All right. I think I want to take a break for 5 minutes, and then I'll continue.